Good morning. Today we'll be talking about equilibrium points in phase space. So we'll start off with what a phase space is. So to define the initial state of any body, we will require the knowledge of any two dynamic variables. So these variables are position and momentum, which we can also use velocity instead of momentum. So a phase space is basically an arbitrary space where any possible initial state of the system that you want to study, you can show it in the graph. So for example, in one dimension, you will need one axis to display position and one axis to display velocity. So but then when we move on to higher dimensions, so if you're studying a three-dimensional case, you will require three axes for position and three for velocity, because for position you'll have the x-axis, y-axis and z-axis, and for velocity also you'll have all the three components. So you'll need six axes, and that will become very complicated to visualize. So next we'll see what an equilibrium point is. So in phase spaces, an equilibrium point is when the velocity is zero and the displacement remains constant. So there are many types of equilibrium. We'll be mainly discussing stable and unstable, which we'll see in the following slides. And there are also other kinds, such as neutral equilibrium. Neutral equilibrium is where the small displacement in the body moving will lead to the body moving, and there will be a new equilibrium point formed. So for saddle point equilibrium, as you can see over here, so the point is where if you move in one direction, you will see that there is a stable equilibrium, and if you move in another direction, you see that it's an unstable equilibrium. And there's the Mexican hat equilibrium over here. So you'll see that it's a ring of neutral equilibrium that goes around, and in any other direction, it is stable equilibrium.
So next we will be talking about phase trajectories and phase portraits. So as time progresses, the velocity and position of a body obviously change, right? And if we follow the motion of this body and plot it on the phase space, we get what is known as its phase trajectory. And because the phase space only has velocity and position as its parameters, we get a graph that's time independent, meaning that we get a relation, a function of v in terms of x. And the set of all possible phase trajectories of a body is called its phase portrait. So now phase trajectories must obey a few properties. The first and very important property is that they cannot intersect themselves. This is due to the fact that phase trajectories are time independent, and we can take any point on its curve to be its initial starting point. But if a body is allowed to intersect its own phase trajectory, it would mean that at that point there are two possible paths for it to follow, which is not possible clearly. And the second is the energy surface. So if we assume that energy in the system is conserved, meaning that the sum of kinetic and potential energy is a given constant, the body cannot simply take any values of position and velocity, but only ones that lead to the sum of these two energies being the constant. And the values of position and velocity that allow this occupy a subspace of the phase space that is known as the energy surface. The third property is periodic motion. Despite the fact that they cannot intersect themselves, phase trajectories can in fact form a closed loop in which the body repeats the same motion over and over again, coming back to the initial point in a given time period.
So now here we'll see the first example, which is an example of stable equilibrium. Here we're taking the potential energy as kx squared by 2, where k is a positive constant, and so the total energy will be half mv squared plus kx squared by 2, which will be denoted by E. And so as you can see in this graph, this is the potential energy graph. It's a parabola, and so this is how the phase trajectory will look. So when the potential energy is 0, the kinetic energy will be at the maximum to make the total energy possible. So that's where the velocity will also be maximum, the magnitude of velocity, so which has both the points, as you can see over here and here. And then when the potential energy is maximum, the kinetic energy will be 0, which will lead to the velocity being 0, and the displacement will be maximum. So that leads to this point. So as you can see, as the velocity increases, the position also increases, and as the velocity decreases, the position also decreases, which leads to the particle moving in an oscillatory motion. So as you can see here, that's how the phase trajectory graph, the arrow that indicates its direction.
Okay. Next we'll be talking about the inverted harmonic oscillator, where we take potential energy to be minus kx square by 2. And if we insert this into the conservation of energy formula, we get mv square by 2 minus kx square by 2 equal to E, which is the equation of a hyperbola. And as you can see, it forms an inverted parabola as its potential energy curve with the peak at x equal to 0. And then if we plot the phase trajectories, we get three distinct situations for the total energy, which is E is greater than 0, less than 0, and equal to 0. So for the first case, if we take E to be less than 0, we get this hyperbola where it's oriented towards the top and bottom of the coordinate space due to the value of, it's just the sign convention, and if we take E to be greater than 0, it will just be orienting left to right. And then we get a third more interesting case where E is equal to 0, where the body forms a pair of straight lines as we get by rearranging the equation again. And this may seem like it's actually intersecting at the origin, which I said wasn't possible, right? But this is actually not the case. Due to the fact that total energy is equal to 0, both velocity and potential energy decrease as you approach this point, but velocity never actually reaches 0. It simply decreases and decreases and tends to 0 and takes an infinite amount of time to reach the origin, which means it doesn't actually intersect.
So this is our next example where we are taking the potential energy to be x square minus a square the whole square. So as you can see, it forms this interesting graph. So first I'll discuss the potential energy graph. So the potential energy graph, as you can see, when x is equal to 0, because we have a constant a, so here the constant is taken to be as 1. So the potential energy will be a to the power 4. And similarly, we'll have two minimas, and at those points at a square. So if we'll start with the first case where the top one.
Which one? Oh, E. Okay.
Yeah. So first we'll take the case where E is less than 0. The total energy is less than a to the power 4, which is this point. So when the total energy is less than 0, the particle can only oscillate from the given positions between the two total energies, right? So that will look similar to the first example we saw, which is the simple harmonic oscillator, which will lead to the particle again forming a kind of periodic motion, and it will keep oscillating. And then we'll see the case where E is equal to a to the power 4. So when E is equal to a to the power 4, we know that x will be equal to 0, right? So that will mean that the velocity there is also 0. Yeah. So you can see that they tend to the center and they kind of intersect there, and they kind of form an infinity symbol. And as the total energy goes more than a to the power 4, you'll see that it forms a kind of periodic motion again, which forms a closed surface. So now when E is equal to 0, you'll see that the graph disappears. This is because x square minus a square the whole square is a positive value, and same way the kinetic energy will also be a positive value. We can't have negative values because otherwise the velocity will be imaginary. So you see that the graph disappears when E is equal to 0. And it just disappears. Yeah. So we'll see the next example now.
Okay. So in the next example, we took potential energy to be x square e power minus x square. So in this case, we get the potential energy curve to be one local minima at x equal to 0, on both sides of which there are local maxima at x equal to 1 by e, I think. Okay, yeah. And then after which the graph tends to 0 on either side of the local maxima. And if we open the phase trajectory of the body, we again get three scenarios. The first is where E is less than 1 by E. Where we get a motion where the body cannot, suppose the total energy is somewhere here, right? And the body can only move up until this value, after which the kinetic energy becomes 0 and then it falls back down, which is shown by these two parabola-like figures on either side. However, if the body begins inside the center before this, it oscillates along this valley over here and it cannot escape. The second case is E is greater than E is equal to 1 by 2E, where the energy is exactly equal to that of the local maxima. 1 by E. Okay, yeah. So it again forms the same cross pattern on either side, which again takes infinite time, as we know. And then the third is where E is greater than 1 by 2E, 1 by E. Sorry. Yeah. Where the body can freely move from either end of the curve to the other end. However, as we can see, the potential energy only tends to zero but never actually reaches zero, which means velocity is always continually increasing at a small rate. So the particle continues moving until infinity, tending to a specific value, which is this. Yeah. Okay, so our last point for today is singularities. So a singular point is a point on the curve which cannot clearly be differentiated and a clear tangent cannot be drawn. Today we'll only be talking about a single class of singular points called the double point, where there are two branches of the curve intersecting. And we can represent the double point as this quadratic C0 plus C1m plus C2m square is equal to 0. And the roots of this quadratic define what kind of double point it is. So firstly, if we get two real roots, it's called a Crew node, which is this one, where the curve intersects itself, and the two real roots are due to the fact that there's two lines crossing and each line has its own tangent. The second point is if there's a single root, and it's called a cusp, which is a sharp turning point. And although it's not clearly visible here, it moves and it appears to form a single line as they converge together at this point, which has a single tangent. And the third is where there are imaginary roots and its isolated singularity or an arc-node, which is this point. And then these are the references. Okay. Acknowledgements. Should I read it? Okay. We'd like to thank IIT Madras, PSBB Schools, Agastya and Pravaha Foundation, and our mentor, Professor P.K. Tripathi, for guiding us. Thank you.
So where would you apply this analysis of phase space to in real life? Like what real life problems do you solve?
Okay. Yeah. Okay. So normally when we're doing like mechanics problems, we get like the force and the mass, and we use it to find the motion of the body, right? But then with phase spaces, we already have the motion of the body, and we can use this to move backwards and like find the force. And okay, and it's just used to, you understand what I'm saying, right? And then we can just use it to observe the motion of a body in general, which is also useful. And I think it has some applications in optics as well to find the path of ray movement. I'm not sure.
But it's very basic. It's like asking what's the application of Newton's law. It's at that level. The point is when you draw the phase portrait, unlike the solution which involves one particular initial condition and then you follow the trajectory, you have the whole class of solutions for arbitrary initial conditions.
How does the symmetry of the space affect the stability analysis of the infinite?
Okay,
Yeah.
Okay, so as you increase the number of dimensions that you consider it in, the number of equilibrium possibilities of the equilibrium points you have increased. So we saw the saddle hat and the Mexican hat equilibrium points, right, over here. So these are only possible in 3 dimensions. Now we only looked at 1 dimension today, but then you can clearly keep on increasing this value, and even as if you increase to like say 4 or 5 dimensions, even for like a saddle hat there are more possibilities with more equilibrium points in the same saddle point. And yeah, it just gets more complicated, so that's why today we only looked at 1 dimension. With these 3 are the only possible.
Yeah, so I actually have 3 questions. So the first one is related to proportion. So could you say that as you increase the number of dimensions, you find a symmetry uniquely? Because for example, the Mexican hat, if you take like a 2-dimensional slice of it, you find like only 2 equilibrium points. When 3 dimensions, you get due to symmetry of the points, you get like a whole like an infinite circle of the equilibrium points. So is that a common solution to
That would probably depend on what kind of So that would probably depend on what kind of motion the body is following. But
So Yeah, also on the slide where you showed the example of x squared minus a squared the whole square, and where you put basically you put x is equal to plus or minus a.
Yeah.
You got that point where is that a true note or is it actually
No, it's not.
No, it doesn't intersect. So you see that it keeps so the velocity keeps decreasing, right? So it never actually reaches zero because the velocity keeps slowing down. No.
Okay.
It is?
No. Okay. So you saw how in the potential energy there was a maxima at this point, right? So we actually proved that at any maxima, the avenue of any maxima near to it, the body behaves as though it's in an inverted harmonic oscillator, and near any minima, it's as though it's a harmonic oscillator. So here you can see the ellipses at the minima and the intersection at the maxima, which is the same behavior as in a harmonic oscillator.
So, what would be phase space of a chaotic body, like say a double pendulum even to flat? Is that just the pseudo random?
What is the double pendulum?
Double pendulum is like two pendulums. Yeah.
I mean, okay. I'm not sure if you can plot phase spaces for two bodies at the same time.
Can we, sir? Yes.
That's a little bit of an unfair question. It's all a question of it. So let me take a problem. He talked about examples. The examples they talked about are one-dimensional examples of Hamiltonian systems, conservative systems, in which the total energy is constant. When you look at dissipated systems in which you don't have a constant total energy, then the possibilities become very wide. One of the big surprises is that you end up with very many possibilities. For instance, you end up with periodic trajectories which are isolated, they are called limit cycles. Once you're on that trajectory, you're on it forever. And surrounding it, there are no other periodic trajectories, etc. And then the big surprise is that when you have a phase space of 3 or more dimensions, you have 3 differential equations that couple to each other, describing the dynamics of variables. Something called a state attractor emerges. So you can have chaotic motion once you have 3 differential equations that couple to each other, even with simple nonlinearities like quadratic nonlinearity, etc. And the most famous one among them is called the Lorentz attractor, which the meteorologist E. N. Lorentz at MIT discovered in 1963. First it was thought to be a computer error, numerical round-off error, but it turns out chaos is a very real phenomenon and it's been extensively studied for the last 50 years. But the beginnings of chaos were already present in Poincaré's work at the end of the 19th century. We recognized clearly that what's called almost any chaos, which at present Hamiltonian systems, is a very, very complex dynamical behavior. So once you have 3 or more dynamical variables, generically you will have chaos. So you have reached the phase space when the trajectory falls and doesn't ever emerge after that, doesn't intersect itself, but it stays in the bounded region. And these regions have fractal characteristics and so on. So very complicated dynamical behavior process. So that's what the lesson of dynamical systems is. What quantum mechanics does to all this is still not very clear. A lot of work has been done over the last 50 years, but we still don't have a full understanding of it. What the quantum mechanical behavior of a classically chaotic system is likely to be. So that's a research where there's a lot of outward research. To summarize, dynamics is complex. Even Newtonian dynamics is extremely complex. Very simple rules can lead to very complex behavior. And I think we will just scratch the beginning surface of the process in this century people are working with that.